project reinforced concrete design adapting the NECP 2010 and 2015. And ang topics na tatalakay natin ngayon are some basic concepts of these balance sections, compression controlled sections, the tension controlled sections, and later is meron tayong isang sample problem lang, no? At least, no, bago tayo pumunta sa mga problem application na pang board exam is at least you know, and you have a heads up, no, of what is this balance section, what is this compression control section, and this tension control section. Okay, so bago tayo mag-umpisa, huwag niyong kalimutang mag-subscribe, no, sa YouTube channel ko para maging updated kayo, no, sa mga susunod na mga videos na i-upload ko dito sa aking channel. Okay, so let's go now to this balance sections, and this will have an introduction that the beam has a balance steel ratio where the tensile steel has just reached its yield point, and at the same time the concrete fiber attains a strain of 0.003. So by this, makikita, no, na yung tension steel natin is nag-yield na siya, no? Just reach its yield point, at saka simultaneously or at the same time yung concrete natin is na-reach na yung strain niya na 0.003. So ito yung section natin na makukonsider natin siya na balance section. Okay? So at the same time silang dalawa, no, sabay nag-yield ang steel, at the same time yung concrete fiber attains, no, this strain of 0.003. Another one is the beam will suddenly fail, no, without giving a warning. Okay, so biglaan yung pag-fail niya without giving the occupants, no, in the building some warning or signs, no, like magka-crack muna siya bago bumigay yung beam natin. So ito ay very dangerous, no, kung ito ang mangyayari sa mga beam sections natin. So it will suddenly fail, no, without giving a hint, no, or a warning to the user or occupant. Okay, so as the load is increased, the deflection is usually not noticeable, no, when having this balance section. So take note of this, no, the deflection is usually not noticeable even though the concrete is highly stressed in compression, and failure will occur without warning to users of the structure. Okay, so ito yung ano niya, no, justification na biglaan ang kanyang pag-fail, no, ng section na ito, ng beam section, dahil itong deflection ay hindi noticeable siya, no. So probably dahil hindi noticeable tong deflection, so more or less yung pagka-crack ng beam is hindi rin napapansin ng tao or occupants. Okay, so this kind of member, no, must be avoided, no, when you are going to design a beam. Okay, so take note of this one. Hindi dapat maging magdi-design tayo ng under dito sa balance section. Okay, so these are just some important points, no, for these balance sections, and we proceed, no, to this compression control, no. But prior to this compression control, take note that this kind of member has a tensile strain, no, denoted by this epsilon t equal now to 0.002. Okay, so ito yung nasa code natin, no, yung tensile strain niya with this amount of 0.002. But yung ano natin dito is 0.002, ang code is nag-allow din siya, no, na pwede siyang maging compression control, no. Makikita nyo later, no, kung itong value na 0.002 ay bakit na sinasabi ko pwede siyang magiging compression control mo na region o section. Okay, so dito naman tayo sa compression control sections. The beam where the concrete has just reached its strain of 0.003. Yung strain ng concrete natin is denoted by this epsilon subscript C before the tensile steel yield. So take note of this one. Yung difference niya ng balance section is at the same time yung pag-fail ng tensile steel section at saka yung concrete has just reached its 0.003 na strain, no? But dito sa compression is ang concrete muna, no? Ang concrete muna has just reached its strain, no? Of 0.003, meaning nag-fail muna yung concrete fiber natin before nag-fail itong tensile steel natin. Okay? So the concrete has just failed first before the tensile steel yields. So ito yung kaibahan dito sa compression control. Take note kung compression control siya, meaning ang concrete mo ay nag-fail muna bago yung steel. Okay? Just as simple as that. And next, the beam will suddenly fail also, like in the balance sections, without giving a warning. No? So halos magkapare-pareha siya sa balance section, no? Na mag-fail siya without giving us or the user some warnings, no? At saka delikado ang design na ito. At saka as the load is increased, the deflection is again usually not noticeable also, just like the balance section, and failure will occur without warning of users of the structure. Okay? And this kind of a member must be avoided, no, in designing a concrete beam. Okay, and this kind of a member is also referred to as a brittle member. Okay, kung brittle siya is mag-fail siya suddenly, no? Hindi tulad kung ductile siya. So meron siyang ductility na hindi siya mag-fail suddenly, no? Kasi ductile siya. But dito is ang compression control section is consider siya as a brittle member. Okay? So take note of this one. At saka itong member na to has this tensile steel strain, no? Denoted by this epsilon T less than or equal to 0.002. So as what I've said, no, doon sa balance section is ang tensile strain niya is 0.002. But ito naman compression control section natin is pwede siyang magiging 0.002 or below this strain na 0.002. Considered siya as compression control section. Okay? At ngayon doon tayo sa tension control sections. So ito yung simple introduction niya, the beam where the tensile steel has just yield, no, before the concrete fiber has reached its strain of 0.003. So kung makikita niyo yung kaibahan doon sa compression, doon sa balance section pala is ang concrete at ang steel mo ay nag-yield siya at the same time, no, simultaneously. At doon naman sa compression control section, nag-fail muna yung concrete niya bago nag-fail yung steel niya. Kaya sa tinatawag na compression control, no? Nag-fail muna yung concrete bago yung steel, but itong tension control or tension control section, nag-fail muna yung steel niya bago nag-fail yung concrete niya. So ito yung kaibahan. Kaya siya tinatawag na tension control kasi nag-fail muna yung tension steel niya bago nag-fail o nag-reach ng strain of 0.003 ang concrete fiber natin. Okay? So yun ang kaibahan ng balance section, compression control section, at saka yung tension control section. So try to remember those, no, because this will be very helpful, no, pag doon na tayo sa application ng problem. Okay? and the beam will not suddenly fail. Take note of this one, the beam will not suddenly fail, giving users a warning of impending failure. So maganda ang design kung nabilong siya dito sa tension control, no? Kasi nagbibigay pa siya ng warning bago mag-fail yung beam, maybe through cracks, no? Cracks from the bottom, and it will suddenly reaches, no, into the neutral axis or into the back fiber bago siya ma-totally fail. So it's a good design, no, kung under siya sa tension control section, and the most preferable section, no, than the balance and compression control section. So ito yung tension control section, and this kind of a member has a tensile strain denoted by this epsilon t greater than or equal now to 0.005. So take note of this, no, because mahalagang maintindihan natin, no, yung mga boundaries at saka limitation ng strain ng every section natin. Kung balance section siya is ang tensile strain natin is 0.002. Kung sa ano naman siya, sa compression controlled is equal or less than 0.002 yung tensile strain natin. But kung dito tayo sa tension controlled section, yung tensile strain natin is kailangang equal to or greater than this 0.005. Okay? So I hope na maliwanag na to sa inyong lahat, no, about this balance section, compression control section, and this tension control section. So dito muna tayo, no, sa mga importanteng boundaries ng ating tatlong sections. So ito yung simple illustration niya. Okay, so ito yung epsilon subscript t referring now to the, this t is referring now to the tensile steel. Okay, it's just equal now to epsilon at subscript ty. Ito yung nagre-refer, no, yung yield point ng ating tensile steel equal now to 0.002. Okay, so sa balance section natin, ito yung ano natin, no, sa balance section. But kung equal or less than siya sa 0.002, nabibilong siya ngayon sa compression control region. But sa balance section natin is pwede tayo gumamit ng tensile strain na 0.002. At kung sa compression control region tayo, pwede tayong gumamit ng tensile strain equal to or less than 0.002. Okay? At ito namang tensile strain natin dito is equal na to 0.005. Yung arrow niya is papunta doon, no, sa right side, kasi pwede siyang more than the 0.005. So ito yung tension control region. So ito yung pre-prepare ng code natin, no, na value ng tensile strain natin is equal to 0.005 or greater than 0.005. Kaya nagiging tension control region. So in between dito sa compression control region at saka tension control region, so ito ang tinatawag natin na transition region, no? Ito yung transition. So posibleng ang values mo dito is greater than 0.002 but less than siya sa 0.005. So ito yung transition region. Okay? And take note of this. The tensile steel strain denoted by this epsilon t values between 0.002 and 0.005 are considered to be in a transition region. It could be either a compression controlled or tension controlled sections. And ito yung halagang formula natin, no? This epsilon subscript ty, ito yung nagre-refer na sa ating tensile steel na yield, at yield, no, na equal to Fy over this modulus of elasticity of steel, and probably we are using 200,000, no, para dito sa ating modulus of elasticity of steel. At ito yung epsilon subscript ty natin is just equal now to 0.002 for grade 280 deform reinforcement. Okay? So, punta naman tayo dito sa table 1 regarding sa ating concrete strain. So, meron tayong ano dito sa first column, no, yung strain natin, tensile strain. At saka sa second column is ang classification at ang ginagamit na mga reduction na factor natin dito referring to this P. Okay? So, types of transverse reinforcement is spiral at ito naman is kung hindi spiral. No? So, para sa ating epsilon Ty, referring now to this yield na strain ng ating tension steel greater than or equal now to this tensile strain epsilon T. So, na mangyayari dito is tinatawag natin siya na compression controlled. Kasi yung epsilon Ty natin is actually equal to 0.002. Okay? At ang value ng tensile strain mo is less than or equal to 0.002, so compression controlled siya. At ang gagamitin mo na reduction factor P kung spiral or non-spiral size ay ito, no? 0.75 kung spiral, 0.65 naman kung hindi. At for the second one is yung tensile strain natin is greater than 0.002, no? Remember na value dito is 0.002 yung epsilon Ty natin, but less than siya sa 0.05. So, under siya sa transition region at ang gagamitin natin na formula for spirals and non-spiral are these formulas here, no, sa table 1 natin. And when your epsilon Ty is greater than or equal to 0.005, so meaning tension controlled siya at ang gagamitin natin is 0.9 kung spiral at saka 0.9 naman kung hindi siya spiral. Okay? So try to remember this table, no? Because this is very useful rather sa pag natin, no? Pag design saka para sa ating problem application. At saka the minimum percentage of steel. So nandoon din to sa code natin, no? So area of steel minimum is just equal now to the square root of Fc prime over 4Fy times your width times your depth, but not less than this 1/4 times the width times depth over this Fy. Okay? At para naman sa ating steel ratio, ang row minimum natin as per code is this square root of Fc prime over 4Fy, but not less than this 1.4 over this Fy. Yung ibang authors ay ginagamit itong 0.25, no? Fc square root of Fc prime over Fy, pero ito talaga siya, no? 1 over 4 yan. And dito naman sa ating row balance is ito 0.85 Fc prime beta 1 times 600 all over this Fy times 600 plus Fy. At para naman sa ating row, ito yung tinatawag natin na actual steel ratio, no? Which is equal now to ES, the area of steel over BD, and which is also equal now to this formula, no, at the right side of this one. Okay? So, take note class na dito sa new code natin, no, sa NSFE 2015, hindi siya tulad sa NSFE 2001 na meron tayong Romax, no? In which ang ating Romax doon sa NSFE 2001 is 0.75 of euro balance. But dito sa code natin ngayon, 2015, walang ini-indicate, no, yung Romax natin is equal na 2.75 euro balance. So mas ngayon, no, medyo mahirap yung bagong code ngayon, no? Mas madali sana kung meron siyang gano'n, no, 0.75 of euro balance kasi may fix na tayo na quantity ng ating Romax. But the 2015 NSFE natin is medyo mahirap na kasi walang ini-indicate na fixed value para sa ating Romax. So nagbabase lang talaga siya doon sa ating tensile strain, yung epsilon T natin. Okay? So another important formulas are, so when we are going to calculate, no, this mu, this is referring now to the required moment, no, required moment equal to P times R subscript U times BD squared. Okay, And ito namang R sub U is equal now to FC prime omega times 1 minus 0.59 omega, at saka itong omega naman is equal now to rho times Fy over this Fc prime. Okay? Okay, so as of this time, ito yung mga important na mga discussions natin regarding the concepts of this balance section, compression control section, and distillation control sections, and some illustrations, and important formulas. So we will go now to our one sample problem, okay, for this day. So we have now this problem statement. Determine the design moment capacity P times Mn of the beam shown given the Fc prime of 27.6 megapascal and Fy of 414 megapascal. So itong P times Mn, meaning nominal momento times your P, ito yung magiging required moment natin later. So ito yung beam dimension na meron siyang width na 375 mm at saka effective depth na 600 mm. Meron siyang 4 pieces of 32 mm diameter bars and the total depth of 675 mm. So magiging approach natin dito is you need to compute the steel ratio. You have to know, kailangan mong malaman yung actual na steel ratio ng section mo, So you need to calculate the rho. Okay, so first rho is equal now to the area of steel over your BD. So meron tayong B na 375 saka D na 600. So yung area of steel is meron tayo apat na 32 mm diameter bars. So calculating the area of steel, pi over 4 times 0.032 squared times 4 over this B of 0.375. Ginagamit ko ang unit dito na meter, times this 0.6 na effective depth. So we can have this actual na rho or steel ratio ng ating beam section na 0.0143. Okay, so after this ay kailangan mo i-check muna kung itong actual na steel ratio mo is nipasya sa minimum requirement ng ating code. So as per the code, ang ating rho main is just equal na to the square root of Fc prime over 4Fy, but not less than this 1.4 over Fy. So you need to calculate this, to comply this. So calculating the square root of Fc prime over 4y and this 1.4 over Fy. So we have this value of rho main when using this square root of Fc prime over 4Fy equal na to 0.0032. Okay? At saka ito namang 1.4 over Fy natin is 0.0034. So take note, ito yung minimum, but not less than. So 0.0032, yung isa 0.0034. Okay? So mas maliit siya kaysa ating 1.4 over Fy, but sa code natin is but not less than this 1.4 Fy. So ito yung minimum natin. Okay? But yung actual natin is more than the rho minimum, so kaya okay siya sa design. So kaya masasabi natin na ang rho na gagamitin natin is just equal now to 0.0143. Okay, so what would be now the next step after computing the steel ratio? Kailangan mong malaman yung values ng ating A at saka yung C. Okay, so after getting this A by equating C equals now to T, makukuha natin yung C by the formula A equal now to beta 1 times C. So dito muna tayo sa A. Since ang compression force natin is equal to tension force, so we have now the 0.85 Fc prime AB equal now to ESFy. So yung area of steel meron na, Fy meron, at saka yung B natin is meron. So the only unknown here is the value of our A. Okay, so ito yung formula at i-substitute natin yung area of steel times Fy na 414, saka ito yung 0.85 times Fc prime na 27.6 times this B na 0.375. Okay, So, ang lalabas dito is 0.151 meter or gagamitin natin mm, so 151 mm. Okay? So, after this, we can calculate na the value ng ating C by using this A is equal now to beta 1 times C. According sa code, ang beta 1 natin is 0.85 for FC prime less than or equal na to 28 megapascal. So, ang ating FC prime is 27.6, so it is less than 28. So, we will use this beta 1 of 0.85. So, substituting this one, 0.151 equal now to 0.85C, we can calculate the value of our C then, which is equal now to 178 mm. Okay? So, after that is we are going to draw the stress and strain diagram. So, makikita nyo dito, ito yung beam section natin at saka ito yung stress diagram natin having this A equal now to 151, 151. Okay, so at saka ito yung compression force natin na C, at saka ito yung tension force, at saka ito yung A over 2 niya, at saka ito yung D minus A over 2. Okay? So, pagkatapos dyan is, ang pinaka-importante dito is itong strain diagram natin. Okay? So, we have this C equal na to 178. Okay? And also, the value of our D minus C is just equal now to 422 mm. Okay? So, yung D natin is 600, 600 minus ang C minus 178, so this would be 422 mm. So by ratio proportion dito is so base dito sa ating strain diagram, ito yung strain ng ating concrete, which is 0.003, at saka ito yung tensile steel natin na strain. So by ratio and proportion, actually this 0.003 over this C is equal now to this tensile, epsilon T over this 422. Okay, so gagamitan natin ng ratio and proportion. So here it is, epsilon ng ating C, ito yung sa concrete, over this C of 178 equal now to this epsilon T of our steel over this D minus C. Okay, so substituting the known values. So, epsilon C is 0.003 over this C, which is 178. So, we are using the unit of meter. So, this is 0.178. Equal now to this tensile strain of your steel over this 0.422. Okay, so we can actually get the value of our tensile strain of the steel, which is equal now to 0.0071. Take note that this is greater than 0.005 kasi doon sa previous discussion at saka sa code natin, kung tension control siya is kailangang equal or greater siya ng 0.005, but this time yung actual na tensile strain natin is 0.0071, which is greater than the 0.005. So we can say that this is a tension controlled section. Okay? So, ngayong alam na natin na tension control siya, so we have now this number 4 step. Now, calculate then the design moment capacity, P times Mn. Okay? So, for tension control, since nalaman na natin na tension control siya, yung P natin is 0.9, according sa code. And then, after that, we are going to use, the tension force. So, you can either use, this T or C. Pareho lang yung result ng ating value. So this time we only use this tension force T. So we have now this P times Mn is equal now to i-times din natin ng P itong T times this lever arm na D minus A over 2. So 0.9, at saka ito yung T natin is ang area of steel, kaya naging ganito siya. Ito yung area of steel natin having this 32 mm diameter bar. So, times Fy, ito yung Fy na 414. Tina-times ko siya ng 1,000, to convert the unit of of this megapascal into kilopascal. Para makukuha natin na unit dito after is kilonewton meter lang. So, times this D, which is 0.6 minus yung A natin na 0.151 over 2. Okay? So, calculating now the value of our P times Mn, which is our design, no? Design moment capacity is just equal now to 628.7 kilonewton meter. Okay? So, this would be it, no, for this problem, and this is our answer, no, for this one. This is the design moment capacity. Okay, so I hope no na meron kayong natutunan ngayon sa video na to, and I hope no na sa susunod natin na mga video is madagdagan pa yung mga kalaman nyo regarding sa subject na to, especially na you're already tackling, no, this ultimate strength design. So sa susunod na mga video, meron tayong additional problems, no, na ipapakita ko sa inyo na hindi lang siya tension control. Mag-ano din tayo ng mga problem na ano siya, compression control or balance design siya, no? So this would be now our next topic, no, the balance, tension, and compression control sections as a continuation of this topic today. And I'm hoping, no, that makikita-kita tayo muli sa susunod na video after this one. And these are my references, the McCormack, the White James, and this National Structural Code of the Philippines, no, NECP 2015. So once again, no, thank you very much everyone for watching this lecture video of mine, and also for subscribing, no, to my YouTube channel. And keep safe everyone, no, and God bless us all.